A few weeks ago, I discussed a fascinating new confirmation of Albert Einstein's famous E=mc² formula, wherein physicists collided two very heavy gold nuclei together, and out popped electron-positron pairs, not from fusion or fission of the nuclei, the gold nuclei, but instead from the photon cloud that surrounds these charged particles. And today I'm going to tell you about an ancillary benefit. As long as we're smashing particles into one another, and maybe engaging in some near misses, perhaps we can investigate some other phenomena that's equally exciting, and this is called Birefringence. Stay tuned for another fascinating episode of Into the Impossible.
Any sufficiently advanced technology is indistinguishable from magic.
So back at RIC, scientists were busy smashing together these gold nuclei and seeing what popped out. But what's very interesting to note is that anytime you have a charged particle, anytime you have an ion, for example, it has an electromagnetic field that surrounds it. That electromagnetic field for a stationary particle will be radially directed away from it. Charges in motion produce a current, and currents via Ampere's law produce magnetic fields. So you have an electromagnetic field when a particle is in motion, especially when they're moving relativistically. We call these potentials advanced and retarded potentials, and they lead to electromagnetic radiation at the boundary where these particles are traversing through space at near relativistic speeds. Obviously, they do that at RIC, the relativistic heavy ion collider. Now, radiation, electromagnetic waves, are polarized in general. And in fact, the polarization of the electromagnetic wave can lead to very interesting phenomena, especially when they pass through what are called dielectrics, pieces of glass, crystals, etc., etc. And in fact, we utilize those properties of photons in many, many varieties. In fact, quite likely the computer screen that you're watching this very video on is making use of the polarized effect of electromagnetic waves. Now, we can also modify the polarization through a variety of different means. One such mean is called birefringence, when you have a photon passing through a linearly polarized photon, or it could be circularly polarized, passing through a medium. Its polarization direction can rotate depending on the properties of the crystal, of the glass, of the material that it's propagating through. What wasn't known until very recently is that this could occur in vacuum as well. So what is birefringence? Birefringence is this passage of light that gets afflicted and affected depending on the polarization of that light passing through the material. Here's a chunk of what's called calcite or Icelandic spar. I'll have an inset from other work that I look at. I show you from the laboratory here. So birefringence is this strange property, acting like it has two indices of refraction. You'd have a very tough time seeing if your glasses were made of this type of material. This is a type of calcite. I've written just the words birefringence on this post-it note, and you can see when I put the crystal on top, you get two copies of the words, and that's just because the paths of each of the polarized light, which is coming from an unpolarized image, which is just the words birefringence. It's just ink reflecting light in different colors, but it's unpolarized. So there's half polarized vertically, half polarized horizontally. And as it traverses this crystal, it will appear to the eye as if the light coming out came from two different directions, slightly offset. The amount of offset depends on a crystal parameter, the birefringent coefficient of the crystal, and also how thick the crystal is. This is a pretty thick crystal, which I got from Superman's home planet. And if you then suppress one of the two polarizations, one of these linear polarizers, you get an image that's 100% horizontally polarized or vertically polarized, depending on the rotation of this axis, and you can actually mix it up. And so the light, being unpolarized, has equal amounts of horizontal and vertical polarization. So when it goes through one of these, it gets filtered. You reject one of those, depending on what axis, how the axis is oriented as I rotate this disc. And you can actually suppress all the light if you have a second polarizer, as I do here. You can suppress all of it, you can transmit half of it, etc., etc. So this is a very cool phenomenon. Now the question is, does the cosmos appear in this exact same way? That's a topic we're going to explore on today's video. This effect was first discovered way back in 1669, even older than me. And I can tell you that this has been a phenomenon that's fascinated me since I learned about it. Birefringence literally means double refraction. It was first accounted for by a Danish scientist who had a very cool name, Rasmus Bartholin. and this took place in 1669 and really perplexed him and many scientists for almost 150 years. So when light travels through a medium like glass, plastic, your lenses, or even this calcite, hunk of calcite here, it gets slowed down. And actually it can get slowed down by an amount known as the refractive index, which is related to the properties in the microscale of these of the composition of the atoms in the crystal. Now, you take the speed of light in vacuum, which is defined to be 300,000 kilometers per second, approximately. You divide that by the index of refraction. In the case of calcite, it's about 1.3. So the speed of light slows down appreciably, 33% or more. So in water, which is another dielectric material, which is translucent, transparent, depending on its state, the speed of light decreases from 300,000 kilometers per second to just about 33% less than that, so closer to 200,000 kilometers per second, owing to the effect of the slowing through the atomic lattice, or through the water molecules in this case, by about 33%. That's the index of refraction of water. Now, in some materials like calcite, you not only get one index of refraction, you actually get two indices of refraction. And the indices depend on whether the light is vertically polarized or horizontally polarized. And there are other materials that can do so for circular polarization, so-called left and right-handed circular polarization. That is the phenomenon known as birefringence. In calcite, Icelandic spar, the question is, where does this arise from? Well, it comes down to the atomic properties of the calcite in this case. It has a crystalline structure that's not cubic, it's not random, and it actually will slow down or relatively slow down one of the rays of light as it passes through, depending on whether or not it's polarized vertically or horizontally. Now, what does polarization mean? Well, light waves are so-called transverse electromagnetic waves. That means their field, the forcing functions that they have, electric field and magnetic field, are transverse to the direction, perpendicular to the direction of propagation. They're also mutually perpendicular in that if the light ray is going towards you, as my index finger is, the electromagnetic field shown in the upper thumb here, that will indicate a perpendicular relationship between the direction of motion, but also the magnetic field will be perpendicular to that. And they'll both oscillate at a frequency corresponding to the frequency of the light that is being propagated. So that's what's called a transverse wave. The force, which is defined as the direction of the electromagnetic field, that's the polarization. The electric field defines the polarization, the magnetic field is 90 degrees to that, and to the direction of motion. That completely constrains the three vectors of propagation and of electromagnetic forces and fields. So it's different from a water wave or from a slinky or something like that. So because light is transverse, you can get two different indices of refraction depending on the polarization of the light. Now, amorphous materials like glass or even liquids like water have relatively random behavior as light goes through it, so there's no need for the electric field to get more affected or slowed down by an effective index of refraction that's greater than for the magnetic field component. So they don't experience that in water and glass and amorphous materials. And even in like regular crystal cubic structures as well, like salt or something like that, you don't get a slowdown in the index of refraction that differs from the vertical and the horizontal, i.e. from the electric and magnetic components. But for things like calcite, this Icelandic spar material again, we have known for hundreds of years that this would actually take place. So it would travel at different speeds in calcite, depending on if the light is polarized vertically or horizontally. The idea that light could be composed of a transverse wave-like phenomenon was first proposed by Thomas Young, a famous Young's double slit fame. And then it was only proven slightly later than that by Fresnel, spelled Fresnel. And we know now that light is a transverse electromagnetic wave. That means it can experience this double refraction, this type of strange behavior. So the crystal structure, in combination with the transverse nature of electromagnetic waves, is responsible for the property that light can be refracted differently depending on its polarization. And this only occurs in certain media, or so scientists thought, until very recently when our friends at the STAR experiment at RHIC, the Relativistic Heavy Ion Collider, decided, I wonder if this effect could take place in vacuum with no crystal, no medium. And that would be as if the vacuum of space inside of their particle accelerator, as if it was depending like a crystal. It was behaving. And that would be like the interior of the Rick star experiment was behaving as if it were actually filled with a dielectric material that was not only possessing an index of refraction, but it had an index of refraction which differed depending on the polarization of light. In some ways, the effect was perhaps no better tested than at Rick. And in fact, this is a consequence of the Bright-Wigner study that we talked about a few weeks ago in our video, Let There Be Matter. So let's go back to the star chamber at Rick. Let's see if with strong enough electromagnetic fields present, as there were when these relativistic ions are coming close and colliding to one another, can we produce large enough magnetic fields to actually polarize the vacuum and make it depend and have a different propensity for the polarization states of vertical light and horizontal light to emerge from these particle collisions. Let's go and investigate what they found. So I'm going to go back and talk about refraction. What is refraction? Well, light always wants to take the shortest optical path. It wants to minimize the action, the so-called action. It wants to spend the least amount of time getting from point A to point B, and if that means it has to go through a medium at a specific angle, that angle is determined by the Snell index of refraction law, as shown on screen. Now, when it changes its path, it will still reach its destination, and it will do so by bending and taking exactly the path that minimizes the action or the distance, or the time really, the principle of least time, to get to its destination. And that is what refraction is. The index of refraction categorizes and characterizes how much the light slows down and bends. You can think about light as a series of wavefronts, and when it enters a new medium, if it enters at an angle to that medium, it will change its direction depending on the relative difference between the index of refraction of the medium that it's now traversing and the previous medium that it was in, usually assumed to be vacuum. Now, in a crystal, you can get two different indices of refraction depending on the crystal structure, as long as it's not a cubic crystal, because a cube looks the same no matter which angle is coming in, as long as the light beam, the direction which the light is traveling, is normal to the face of the crystal, and you can always rotate the crystal so that the face that the light is impinging upon is perpendicular to the light travel direction, and therefore perpendicular to both the electric field, which is defining the polarization state by convention, and the magnetic field at right angles to both those vectors. And so because the index of refraction changes with the polarization of incoming light in birefringent materials, so too does the amount by which the light refracts for these two different polarization states. This is called birefringence. You can also get another example that's sort of allied called Faraday rotation, or the Faraday effect, or circular birefringence, and that's usually obtained when you have a magnetic field present that's energizing a plasma, for example, and that can create a rotation of the plane of polarization as well. And in fact, we are going to plan to use the Simons Observatory and other experiments to look for the earliest magnetic fields in the universe by using this Faraday rotation effect. For polarization calibration, I'll go on the top of the instrument to calibrate the faint CMB B-mode signals that we're hoping to see. When an electromagnetic wave, say light, is impinging upon a medium through which we've suffused a magnetic field, the rotation of the plane of polarization will change depending on the strength of the magnetic field and the properties of the medium in which it's traversing. It will rotate. That's called Faraday rotation. Now, in the Rick experiment, you can also see a circumstance where the magnetic field interacting with a photon could also take place, thus providing an opportunity for the circular birefringence phenomenon to be exhibited. So the photons that come together, engaging in these collisions, are linearly polarized. This is exactly the same type of polarization property that we explored when we talked about birefringence in crystals like calcite earlier. Now, because these photons come together over such a brief amount of time, these collisions are occurring at relativistic velocities for both of the nuclei that are coming together. So you'll get a random orientation of the photon polarities, and then you can measure the outgoing distribution of their polarization states. And you can compare. Is the outcome also, on average, is it unpolarized? Equal amounts of horizontal and vertical polarization. And that's what the researchers investigated. So vacuum birefringence would say that in a vacuum, in a strong magnetic field applied to it, photons can emerge and they can be differentially rotated. They can have a difference in angle behaving as they emerge at different angles. They can emerge differently, just as if the vacuum now, this is in a chamber that's completely evacuated in a laboratory, pumped out. There's no crystals in there. There's nothing in there. So you're seeing a double index of refraction by refringence in vacuum, thanks to the magnetic field polarizing the vacuum. This is a fascinating phenomenon. And the index of refraction will differ depending on the polarization of and the distribution of the light that's emerging from these interactions. So it looks like a birefringent medium. It acts like a birefringent medium, and therefore it's quacking just like a birefringent medium. So it's plausible to say that a polarized vacuum, strongly polarized with a magnetic field, behaves almost as if it's a crystal, except it's a vacuum. So it's almost as if we have polarized the vacuum. That's exactly what researchers have claimed to discover at RIC. Now, it's interesting to note that the scientists who initially described this process and started talking about this photon-photon reaction producing the particle-antiparticle electron and positron pairs, Bright and Wheeler, never thought this process would be detectable. So I'm showing here from a slide talk given at CERN, this shows the classification of various fundamental interactions between light and matter. And you can see one of them shown in the lower side. On the lower right is the Bright-Wheeler process, where we have this exchange of two photons coming in and out go an electron-positron pair. And again, this phenomenon can be classified and also seen as an allied phenomenon to this vacuum polarization phenomenon. So here we see a description of vacuum magnetic birefringence with a term that's unimaginably small and was thought never to be observable, and in fact may never be observable. So we can discuss birefringence, vacuum birefringence. Now, birefringence can take place at the quantum electrodynamic level. So birefringence of the QED vacuum is shown here. We see great detail shown here, the geometry of what takes place in the STAR experiment. And you have what's called a probe photon, which is called probe gamma, and an outcoming gamma that comes out, the observed gamma, and they're rotated by some angle. That's the birefringence. That's a rotation angle due to the polarization of the vacuum by the applied magnetic field. So by measuring the tiny differences between the polarized angle that emerges from the input polarization angle and comparing with this theoretical prediction of the type of modulation that should take place, the researchers reported the first Earth-based observations at a very high almost 7 sigma statistical significance level of vacuum birefringence. It shows that nature is very strange and the universe may not be exactly the way that we conceived it, that we can measure such minute effects in total contrast to what Bright and Wheeler predicted, as shown here in their 1930s paper. Now we're measuring these things almost 100 years later. The creativity, the cleverness of these experimental physicists is quite unimaginable, and we can only imagine where we can go next. That the universe itself could possess a type of birefringence, that the universe could act as if it is a giant crystal. Obviously there's no crystal, there's no ether, there's no spheres, sorry Aristotle, but instead the universe could manifest a tiny little divergence from perfect symmetry for vertical and horizontal polarized light. And in so doing could behave as if the universe is birefringent. And that could have ramifications not only for our understanding of electromagnetism, but for our understanding of what is known as Lorentz invariance violation. A topic I talked about with Sean Carroll in 2020 when there was a tentative claim made only about the 2.3, 2.4 sigma statistical significance level, far, far lower than the RIC experiment is claiming. And this, by researchers Miami and Komatsu, is still being investigated, and it's something that we hope to follow up with projects like the Simons Array and the Simons Observatory. This instrument, we hope, will take us back to the beginning of time, perhaps. So stay tuned. Maybe the universe will be found to have a twist to it. The universe has been twisted in the past, and there's no reason not to think that our best limits on so-called cosmic birefringence of the vacuum of Einstein, of interstellar space, could also possess this behavior, and that would turn physics on its head, because the underpinning of all of modern physics is predicated on symmetry known as Lorentz invariance. So violating that would have huge ripples for quantum mechanics, for relativity, and for our understanding of what are called the standard model of particles, forces, and fields, and our standard model of cosmology. So stay tuned for upcoming experiments and results from projects like the Simons Array, the Simons Observatory, the Bicep Array, and other projects studying the largest laboratory in the universe, which is the universe. For now, I'm Brian Keating, Chancellor's Distinguished Professor of Physics and co-director of the Arthur C. Clarke Center for Human Imagination, thanking you for going into the impossible. If you want to learn more about Lorentz invariance violation, watch this video with me and Sean Carroll. Otherwise, click here and see conversations with 9 Nobel Prize winners and more on my Think Like a Nobel Prize Winner playlist.